The basic principles of meshing of two involute gears have already been explained in detail in the linked video. In this video, we will take a closer look at a special case of a gear wheel, the rack. The meshing there will make it easier later to understand the profile shift. The animation shows the meshing of a driving gear wheel with a rack. The rack can ultimately be regarded as a special case of a gear wheel with an infinitely large diameter. The curved shape of the tooth profile changes into a straight shape. The faces of the straight teeth are inclined to the vertical by the standard pressure angle α0. The line of action is also at this angle as it is perpendicular to the tooth faces. As usual, the line of action is tangent to the base circle of the gear and is therefore clearly defined. As with the meshing of two gears, the actual line of contact begins at the intersection point A between the line of action and the tip line of the driven rack. The end of the line of contact is again defined by the intersection point B between the line of action and the tip circle of the driving gear. The pitch point C is to be determined analogously as the intersection between the line of contact and the center line of the two gear axes. Since such a center line always runs in the radial direction of a gear and therefore always perpendicular to the gear surface, the center line is therefore perpendicular to the rack. The position of pitch point C is therefore also clearly defined. The pitch line of the rack and the pitch circle of the gear touch at this pitch point. With no backlash, both sides of a tooth on the rack are in contact with the teeth on the gear. But if there is a shift in the radial direction, there is backlash. However, this does not change the position of the line of contact, which is always perpendicular to the rack teeth and tangent to the base circle of the gear. Neither the base circle nor the tooth angle changes, so the position of the line of contact does not change. The position of the pitch point does not change either, as the center line does not change. The only effect of a radial shift of the rack is a shortening of the line of contact. The invariable position of the pitch point is also immediately apparent from its definition. The pitch point is defined as the point at which the circumferential speeds of two gears are equal. In the case of the rack, however, this is a translational motion. Every point on the rack, therefore, always moves at the same velocity, regardless of the distance to the gear. This means that the pitch circle on the gear wheel, whose points move at the same speed as the rack, does not change. The pitch circle remains the same, and so does the pitch point. This is particularly important when manufacturing gears with rack-shaped tools. The animation schematically shows the machining of a gear wheel with a hob cutter. The profile of the hob corresponds in principle to that of a rack with its straight flanks. These straight flanks do not require a complex geometry of the cutting edges, which makes the production of tools for involute gears relatively inexpensive. The already mentioned profile shift in gears now corresponds to the radial shift of the tool profile during gear machining. The effects of this on the tooth shape are shown in the animation. As with the shifting of the rack, the shifting of the rack-shaped tool profile always results in the same pitch circles on the gear. These are then also referred to as manufacturing pitch circles. The illustration again shows the position of the rack-shaped tool profile during the machining of a conventional gear wheel. The distance P0 between the straight flanks corresponds to the resulting circular pitch on the gear wheel. If the tool profile is now shifted, this has no effect on the distance between the straight flanks of the tool. Therefore, the same circular pitch P0 is also produced on the profile shifted gear on the same manufacturing pitch circle. These manufacturing pitch circles correspond to the reference pitch circles of the gears. Both conventional and profile shifted gears therefore all have the same reference pitch circles or circular pitches, provided they are all manufactured with the same rack-shaped tool. The reference pitch circle as a manufacturing pitch circle is therefore a fixed, unchangeable parameter of a gear that is determined solely by the rack-shaped manufacturing tool. So note, the reference pitch circle of a gear corresponds to the manufacturing pitch circle in gear production with a rack-shaped tool. Although it is not obvious at first glance, the tooth profile in both cases is an involute with the same base circle. This becomes clear when the two teeth are positioned on top of each other. The shape of the involute is ultimately determined by the inclination angle of the flanks of the tool profile, which in both cases corresponds to the standard pressure angle α0. As a result, conventional and profile shifted gears not only have the same reference pitch circles, and therefore the same circular pitches, but also essentially the same tooth shape. For these reasons, conventional and profile shifted gears can easily mesh with each other, provided they have been manufactured using the same rack-shaped tool. We will go into more detail about profile shift and its advantages and disadvantages in another video.